One of the problems that I run into with flat earthers is their inappropriate demands for particular tests or measurements. For example, they only accept physical measurements, i.e. with a tape ruler. They won't accept mathematical determinations. So I got to thinking the other day, what if I could measure the Earth with a tape measure? I wonder if that would be good enough for them. Well, let's find out. Ladies and gentlemen, here is a direct measurement. This is the Southern Cross Cable Network. It is a series of undersea cables between Australia, New Zealand, Fiji, Hawaii, and the western United States. The origin and destination of each of these cables is documented, as is the length of the cable. They are a direct measurement of the true distances between land masses on Earth. Now, this is one segment of that Southern Cross Cable Network. It goes basically from Sydney to Auckland. Specifically, it goes from Alexandria, New South Wales, to, forgive me if I mispronounce this, but Winnipeg, New Zealand. So how do we determine how far it is on a flat Earth between Alexandria and Winnipeg? Now again, since this is a flat surface, we can use Euclidean geometry. If we draw a line from Alexandria to the North Pole and calculate the number of degrees between Alexandria and the North Pole, we can calculate the length of this side of a triangle. Now, the coordinates for Alexandria are 33.9 south, 151.2 east. So to get the distance, it will be 90 to the equator plus 33.9 times 111 kilometers. That distance will be 13,752.9 kilometers. Likewise, we can do the same for Winnipeg. The difference in longitude between Alexandria and Winnipeg is 23.4 degrees, so that's this angle at the North Pole. We now have a side angle side triangle, and we can use something called the law of cosines to solve for this third side of the triangle right here. On a flat Earth, that should be the distance between the station in Alexandria and the station in Winnipeg. Now, the law of cosine says that c squared, and c is the side that we're looking for, equals a squared plus b squared minus 2ab times the cosine of this angle of 23.4 degrees. Let's go ahead and do the math. Well, it's kind of a handful, but it's 1352.9 squared plus 1474 squared minus 2 times 1352.9 times 1474 times the cosine of 23.4 degrees. That'll give us the square of c. Then we need to take the square root of that number, and that gives us our final answer. And in this case, it's 5,651.9 kilometers. So on a flat Earth, that's how long the cable has to be to go between these two locations. Now on a spherical Earth, we use something called the Haversine formula. Now if you thought that the law of cosines was a mouthful, let's look at the Haversine formula. The Haversine of the distance between those 2 points is the sine squared times the change in latitude over 2, plus the cosine of lat 1 times the cosine of lat 2, times the sine of the change of longitude over 2. Now once you have the Haversine, we actually need to do a little more to it. To get the distance between the 2 points, you take 2 times the radius of the Earth times the arcsine of the square of the Haversine, because the Haversine is a sine squared. Now, we can go 2 routes with this. Now, if the radius of the Earth is known, we just go ahead and solve for the distance between the 2. If the distance is known, we can actually rearrange this a little bit. That's right, if we know the length of these cables, we can simply calculate the radius of the Earth directly. But we've already determined the radius of the Earth by other means. So we're going to go ahead and just calculate what the distance should be on a spherical Earth between these 2 points. Now, when you bring all this math together, we find that the great circle distance should be 2,141 kilometers. We've already calculated the flat Earth distance as 5,651.9 kilometers. What's the actual length of the cable? Based on published records, the cable length between those 2 locations is 2,276 kilometers. Okay, what's this tell us? Well, first of all, the minimum distance it could be on a spherical Earth is 2141. If it's anything greater than that, that doesn't rule out a spherical Earth in any way, shape, or form. However, on a flat Earth, the minimum distance has to be 5651.9 kilometers. The bottom line is this length fits the spherical Earth, but it is impossible to stretch 2,300 kilometers of cable to 5,650 kilometers of distance. This conclusively rules out the possibility of a flat Earth, and it strongly supports the evidence of a globe. But wait, there's more. We have another section of cable that goes from Brookvale, New South Wales, up to Suva, Fuji, and that is between points number 2 and point number 3. Let's go ahead and do the same thing for that. Here are the coordinates of Brookvale. Here's the coordinates of Suva. The flat Earth distance is 6,344 kilometers. The spherical Earth distance is 3,227 kilometers. If the actual distance of the cable is less than this number, it rules out the flat Earth. What's the actual distance? (3,540 kilometers). This is impossible on a flat Earth. It is completely compatible with a spherical Earth of radius 3959. And as my friend Sci-Man Dan likes to say, done and dusted. This is Bob the Science Guy. Follow me for more like this. Flat Earth tears, extra salty.